use over on the boards and the contactors that we use over on the boards, so that you guys will be prepared to be able to get that done. So we're going to look at a couple of simple ladder logic diagrams and some of the parts. So I have one of the switches up here. Should be able to get that up on the board here. You can look at it. We get an actual light coming up. There it is. It's a toggle switch, or we call them limit switches. Some people call them micro switches. They go by a number of different names, but when you look at what goes on, there's the actuator. Up and down, there's a little button under here that gets pushed. I don't know if you can see it, a little button there that the actuator actually pushes as it goes down. There are 3 terminals on this particular switch, and if we look at the terminals on the bottom, we can see the one on the right-hand side over here says normally closed. We have one right here that says normally open. Let's see if we can focus that a little bit better. Normally open, anytime. Normally closed, normally open, and this one's listed as common.
Could a switch like this be used for like jogging? You know, if you were just doing like a momentary, because isn't jogging, you're just doing kind of like a short
momentary, yeah, that's what jogging is like moving a motor a little bit forward, a little bit back to get it adjusted properly.
Could you use this kind of a switch for that?
Not normally.
Okay.
It could be used for that because it has an actuator that you can press, but normally the way these things are used is they're mounted to some frame piece, like over on the 3D printer, and something comes along, like a copy machine carriage comes along and click, and it knows when it gets to that point that it's in the home position. So it stops the motor. When you press a copy cycle, it goes over, makes the copy, and then comes back and says, okay, click, I'm home. And it knows, the motor then knows to stop turning. So these are normally switches that are activated by some mechanical device. But there's no reason that you can't press it with your finger.
Yeah.
There are better switches for that purpose. Okay, so what that looks like on the board, schematically, is this. Here's the switch. And let's make sure and draw it in the proper orientation. We'll draw it this way so that the prime is coming off like this. And here we have a common. We have normally open and normally closed. Okay? What that means is we have a common coming into an actual switch. Normally closed, normally open. Single pole, double throw. Okay, it basically switches one signal, and it can switch to 2 different places. Okay, so as you can see, these are mounted on the board in this position, with the tongue or prong aiming to the right. I think the other board is wired the same way. I can't quite see from here, but I think the other one on the right is wired the same way. So that should be a standard. Okay, when you press the lever, what happens? When the lever's pressed down, the normally open becomes closed, the normally closed becomes open. Okay, any questions?
So that's just with the single pole?
Right. These are just single pole switches. They take one input and send it to one of two places.
Oh. So there's no setting on it that you can just switch the, what you just said, where one is normally open and closed?
Yeah, there is a setting. This thing right here switches the connection.
Oh, okay.
That's how you move this back and forth.
Oh, okay.
Right? So when I press down on the switch, what I'm doing is here, there.
Oh.
See that?
Oh, yeah.
Okay, what is this really for in the context of our boards? We do use these switches, but let's keep in mind that these switches actually mean a number of different things to us. I may give you an assignment that says, turn the motor on when the temperature gets to, say, 70 degrees. How are we going to model that? Well, in the real world, I'm going to have a temperature switch that is going to switch or make contact at 70 degrees. Or I may have a float switch that will make contact when the water reaches that. There was one laying around here, a red, nice pretty red one laying around here somewhere. When it gets to, when the float switch reaches a certain point, it will switch on. What this does is it allows us an inexpensive and easy to replace way to simulate that condition. So our eyes see a manually controlled switch, but what we should be looking at is that that manually controlled switch can represent any number of different conditions that go from not acceptable to acceptable, or acceptable to unacceptable. Temperature gets too hot. Temperature gets to be just right. We can simulate that with this. And that's the type of thing that we'll do over there. Okay? As an aside to our discussion now, but it is appropriate, one of the other things that you have on those boards over there is a series of 4 lights. I think there's 4. L1, L2, L3, and L4. What are those lights for?
They represent the loads
They represent loads.
of whatever they want, whatever we would want them to be.
You're probably not going to go into a factory anywhere and see a ladder logic circuit that's sole purpose is to turn on lights. That's not industry model. We wouldn't see that in the real world. But what we would see is a ladder logic control board that's used to control a heater or a motor or any number of other types of equipment, many of which would be very expensive for us to bring in here so that you guys can learn how to turn them on and turn them off. That causes problems. If you hook it up wrong, you've destroyed an expensive piece of equipment. So those light bulbs, inexpensive way to simulate a load. Simulate a stirring motor turning on, simulate a conveyor belt. Okay? Maybe you're going to make some cookies, and as you make cookies, you put the dough out, so you have one light that flashes like this to show that the dough is being put onto the conveyor belt. You have another light that indicates the rotation or motion of the conveyor belt. You have a third one that indicates the condition of the heater, the oven element, heating element. So you can really model that whole process on there with 4 light bulbs.
Take notes on that, because that's our final lab.
It is a lab towards the end. Yeah. Okay, and there is actually another project where we do use these as light bulbs, and that would be, of course, the Venerable Traffic Light Project, where you come up with a way to generate traffic lights. And you might have to use both boards, one for north-south and the other one for east-west, and wire those 2 boards together to make that happen. So that is down the road. Okay? In the meantime, we still have a couple of things to look at today. We've looked at these switches. We've discussed the light bulbs. There's not a whole lot really to discuss when it comes to a light bulb. It's either on or off, which is pretty much what the point is. The third thing that we need to be aware of is really more of a safety issue than anything. And that is that if I have a person who is at the control panel controlling something, we don't want that person to be working with high energy. We want the high energy to stay over here. And what we want to use is low energy to control high energy. Okay? And seeing this in action is as simple as looking in an automobile. You have the cabin where the driver sits, and you have the engine bay. And in between the two, what do you have in between the cabin and the engine bay in the car? For those of you in computers, this should be a very familiar term. In fact, it's where the computer term came from. And the term that we're talking about is firewall. Okay? I have a firewall in between the two. In old school version, before computers, a firewall meant a division through which nothing in the engine compartment could go back and hurt someone who's driving the car or flying the plane or working on the equipment. Okay, so in some way we have to use low energy, which interfaces with a person because low energy is more safe than high energy. And we need to use low energy to control that high energy. We do that in the car, for example, with the headlights, which run 10, 15 amperes sometimes, which is a lot of energy. We use what's called a headlight relay. When you turn the headlight button on, all you're doing is kicking another button, basically, that's in the engine bay and telling it to conduct the current required to turn the headlights on. Same thing with the starter relay. If you use 300 amperes to start your car, because batteries have, what, 400 cranking amperes they talk about? Have you heard that term before? This battery has 475 cranking amperes. What does that mean? That means it can output 475 amperes long enough to start your car. Do you really want that 475 amperes coming up through your steering column, right where your hands are?
Oh yeah, sure.
And then out? No, we don't want that. So we use what's known as a relay to make that happen. We'll talk about relays in a further, later lecture. But today we're going to talk about, actually we're going to talk about the relay's bigger brother, the contactor. Let's back off of this. I said back off. There we go. Let's see if we can work with the lighting a little bit here. There we go, we can see everything. I don't know if we can turn the light off and sustain visibility. Looks okay, doesn't it? Can everybody see it? Mm-hmm. This is a contactor. It has two inputs up here, which are called the coil inputs. And then it has a whole bunch of connections, which can look rather confusing, but it's really, really very simple as to what's going on here. Okay? Notice, normally open, normally closed, normally closed, normally open. two normally close together, right?
Yeah.
Okay, you'll notice that there are some screw connections that are viable. You can connect to them, but we're not going to use these up here. That's why they have X's in them. And we're not going to use these down here. We're only going to use the sets that are on the upper block. You can kind of see what we're looking at here. If I look at this from the side, you can see that there's a upper block and a lower block. We're going to connect to this, but we're not going to connect to that. I'm never going to be able to get it back to the way it was, am I? Yeah, it's pretty close. Okay, so when you look at purchasing a contactor and you look at the coil voltage and the voltages that these things handle, when we look at this, we might say this has a coil voltage of 120 volts. That means it will run off of the line voltage in the wall. We might also find a contactor that has a 240 volt or a 24 volt contact, a DC. Have to have the right one. We had to order all of these because all the ones that we had were 240 volt ones that are used in the other room. So we had to order the 120 volt connector contactors like this one. Okay, so when we apply 24 volts, 240 volts, or in this case 120 volts to that coil, what happens? Well, what happens is this coil generates a magnetic field that pulls against these, drawing this here, drawing this here, drawing this here, and drawing this here. This one closes. This one opens, this one opens, and this one closes. Questions so far? I have this on video, so you'll be able to watch it. At least I hope I have it on video. Questions, Dawn? What we have here?
Not this one, no.
Well, which one then?
There's one in the, it's in the activities, I think it is, that, and it's a motor system set up with a couple of contactors and an overload switch, and it gets into, and I was talking to Robert about it, it gets into if the overload switch is triggered, if they restart it, does the motor run? And I'm like, it doesn't tell you how the overload switch works, if it's manual, if it's got some kind of auto reset or whatever, and Robert said it's usually a manual.
Yeah, in some case, a lot of, it depends on what you buy.
So the way I was looking at the circuit, I'm kind of we've got to work on it today, because I kind of don't get it.
Well, and we're going to end up talking about that as well, but basically the way that works is if I were, let me go get it. Let me see, do I have a screwdriver somewhere? Maybe over there.
Because it has a contactor, it has a motor, it has an overload switch, it has a normally open and a normally closed switch, and a LED. So in my mind, some of it looks like it would always have power, because it's...
Okay, here is the motor setup. Okay, all this is, if you look at this here, this is just the same as that with this piece removed. Okay, so it's exactly the same contactor that we're using. This piece that we put on this contactor is an expansion module, because the contactor itself only has normally open. All of these are normally open. So what we do is we connect into the coil, which is this push button here, and that reaches into the back and pulls on this, so we can multiply and change the configuration of the contactors. This one, however, since it is a motor protection, we only need the normally open version, because there's no reason to ever keep it closed and then open it. This is designed so that when the coil gets energy, the motor turns on, right? 3 phases, 1, 2, 3, L1, L2, and L3. Here is our temperature adjustment. This is our sensitivity adjustment that we can make right here. And there's a reset button.
Now, is that the, what's the temperature that it's reading? I mean, is it reading,
I'm not sure. It doesn't say.
Is it reading the air temperature? Is it reading the temperature of the wires? Or is it reading...
I think it's the motor.
It's reading the temperature of, it's reading the current, the temperature that's generated by the current in the wires. It works the same way that a circuit breaker works. It's always based on heat, right? Who writes the code? National Fire Protection. So of course everything's going to be based on heat. So that's something that a little bit later on in the course you're going to have to figure out how to hook these up.
Yeah, that'll be the making cookies.
And the nice thing about it over here is that you're only working with a single phase. This is the 3-phase compatible. You don't have to use all of them, but if you thought about this as having 3 normally opens, then you could use them as a 3-phase connection. 1 to control, 1 phase to control 3. And that's what you see on your motor controller. Okay, a lot of times on your motor controller what you'll see is this. You'll see that you have 3 phases, L1, L2, and L3. And L1 does all of your ladder logic. Generally, all your ladder logic is done with 1 phase. Okay? And then what we'll do is we'll take L1, L2, and L3, and we will put them into a normally open setup, 3 of them, together, all controlled by the same coil, L1, L2, L3. There's our contactors, right? And then you see a little thing that looks like this. Have you seen that in, I'm not very good at drawing it, but have you seen that in your drawings? It kind of looks like that. That's your heat sensor, or the motor protection. That's this guy. Okay, so this drawing that you see represents that contactor. And that's similar to the drawings that are represented in the book when it shows 3-phase motor control. Okay, questions? I want to go back to the other contactor. Does that answer your question for now?
No.
No? Well, then ask again.
No, no, I'll ask you later, because it's the actual circuit that
Oh, okay.
I'm looking at that's kind of messing with my head.
Okay. Yeah, we'll look at that separately. Okay, when you guys get ready to make your circuits and do your thing with your circuitry, and you look at this contactor, one of the first things that you're going to want to do is, especially if you're using more than one, give it a name. This would be CR1. Coil 1, coil 2, they don't have any numbers or anything on them. What's really nice is the other terminals on here already have numbers. Okay? But to address ones that don't, I'm going to call this A, B, C, and D. So if I were to make a circuit that makes use of this entire contactor, and let's actually use the right way to do it. The first one is normally open. And we're going to call this CR1-A. And 53 and 54. CR1-D is 83 and 84. Okay, we have a limit switch that we press, and from what we've shown, CR1, that's CR1. We may as well just go ahead and put this guy in there too. This one's M. And it also has a coil 1 and a coil 2. And then the rest of it would be as we showed it before. 1, 2, 3, like so, our motor. And then, of course, before we get there, we've got that get an idea of how that's laid out. Okay, the important thing to concentrate on for today, and I think I must have messed something up here, is this normally open, normally closed, normally closed, normally open. Do I have these wrong? CR1A, normally open, CR1D, normally open, and CR1B, yeah, that's right, normally closed. Okay, so we're good.
Open, close, close.
So how does this work? What's going on? Let's talk about shelf state. What happens when the switch is not energized?
Mr. Lanning, on your contact, normally close is 61 and 71?
I'm not using that one.
Oh,
I'm only
okay.
using
I'm looking at
3.
the wrong one.
I'm only using 3. I'm using A,
Oh.
D, and B.
I figured that first one was your SW switch, one switch.
No, that's this thing.
Oh,
This guy. That's our switch.
oh, okay.
That's the part we covered when you weren't yet here. You want to take a look at it? Ah! There it is.
Cheek's gonna be all up in there.
Okay, so the motor's on in shelf state. What does switch 1 do? Turns on 2 lights and turns the motor off, doesn't it?
Mm-hmm.
You see that, Terry?
Oh, okay, so... Oh, because I thought CRB, when you have the crossroad like that, it's closed right now.
It is.
Oh, it's closed. Oh.
It is. So what's going on right now is, here's where we have the energy. Energy is going to that coil, which means that all of those are closed and our motor's on.
Oh, okay. Oh, I see.
Okay, as soon as we press the switch down, what happens?
All
Energy
contacts
goes here to
reverse.
this coil, closes this, closes that, and opens this. That means that energy goes to our one light, energy goes to our other light, energy does not go to our coil, and energy comes to here but does not go past that point, because these are now open. Normally closed, normally open. Okay, those are normally open contacts, which means that now that the coil to the motor is turned off, these will be open. Okay, so you always have to look at shelf state. Shelf state means, what is it right now? If I were to take a ohm meter right now and ohm out the normally open contacts, I would see an infinite amount of resistance there, hopefully. And if I ohmed out the normally closed contacts, since they are normally closed and this is a normal condition and it's closed, I should see roughly 0 ohms. When I switch it, which I can simulate by pushing that button, then everything should convert over to its non-shelf state or active state, and the closed will become open and the opens will become closed. Okay, so what is it really? Just a big switch. It's a big remote-controlled switch where we can take a very small amount of energy and control the coil and use larger amounts of energy remotely on the other side of the firewall. Okay? Is that circuit that you wanted to look at in the green book?
Yeah, it's like activity 2, I think.
Mm-hmm.
Let me see if I can bring that up here.
Okay.
I should be able to. Activity 2.
Yeah, I think it's activity 2. Or was it activity 1?
2.
2.
What day was it?
Don't have a clue.
Activity 2, you're saying? You think it was activity 2?
Yeah.
Yes.
Keep going, keep going, keep going. Keep going. Right in there. Because pertaining to those two drawings, they're asking questions on it, and
So basically, after you went through
Top one or bottom one?
the bottom,
the bottom one.
You want to look at the bottom one first? Okay, well, let's make it bigger. Oh, we're not on the camera. Did you catch that on the video? Yeah, it's one of my shining moments, right? Yeah. Okay, we should be able, can we all see that now? Is it big enough for everybody to see?
yes.
Okay. All right, so what's going on right now?
So in my mind, in shelf state, as you put it,
Okay.
there is power going through the stop, down. Obviously, it doesn't pass the open state, so that would activate that.
That's where we are right now,
It stops, right?
right?
So why does it stop?
Because it's not
It's
closed.
already, it's stopped right now.
Yeah, the contact's not closed. So it has to be
Okay.
energized.
Now, let's go through the sequence of events.
I guess my question is, how is the coil not energized if the power is getting there? How does it get, because it looks like the way it's drawn, that it bypasses the start switch. It should go right through the coil, energize the coil, go to the pilot light and the motor.
No, but it doesn't. Look at
Right.
this. What is that?
That's,
What's that?
that's open.
That's open.
It's open, so nothing's
It's
going
not going
past
there,
there. It
yeah.
can't get through there, it can't get through there. Two
Right.
bridges are out,
Right.
right? Here's what happens. We press down the start button. As
Yeah.
soon as we press down the start button, this bridge opens. That goes to our M,
Mm-hmm.
which then closes this and allows, well, this all would have flown at the same time.
Well,
But now, what's happened is, I pushed down that start button, that energized the M, right? And that also closed this, which means I don't need the start button anymore. So now that the start button is gone, I still have a contact here that's holding that coil open, or holding that coil closed, and holding the pilot light on.
so is the contactor wired directly to the start button? I mean, it doesn't, the way it's drawn to me in my mind, it's not wired into the start button, so the power gets there. And I guess I'm just not getting why it's activated when the start button goes down.
Well, you remember how a relay works? How if a relay is energized and anything is open, it'll reverse the contacts for that particular relay. So that M is a relay, but it's not energized because the start switch hasn't completed the circuit yet. So now it's an open circuit. So once that switch is pushed, all the current will flow, and then it'll reverse the contact down there on your wire 2 and 3.
Well, I guess because the way I'm looking at it is it could bypass the start button. And why doesn't the power, when it gets there, energize it?
It can't bypass the start button. I don't know where you're getting that from.
Well, I mean, I don't understand why if the power gets to the contactor, why it doesn't energize the contactor.
It does energize the contactor. That's the part that you're missing. And I'm going to try and redraw it now, and I'm just going to do it a little bit differently. No, I guess I'll keep it the same.
On one
Then
side.
we have down here, we have a set of contacts and a pilot light. Right? And then there's a connection here. Okay? So, how are we starting? When we start this whole thing out, what is the shelf state?
The shelf state, in my mind, is the power goes from L1 across the normally closed and then down to the contactor.
All right, here's the shelf state. Okay? Energy is going where?
Across the normally closed
Across the stop,
and then down.
right? And right to there.
Yeah.
And it's going down and right to there. Okay, since there's no hash mark across there, that's open, right? So it can't get through. This is open, the start switch, because we haven't pressed it yet. So it can't get through,
Yeah.
which means that you have nothing here.
Yeah.
Okay? Number 2, press start.
But why doesn't, I guess I don't understand how the contactor itself is actually activated, because in my mind, the way it's wired.
No, here's what you have. Here's your contactor. Remember this? We have a coil,
Yeah.
and in this case, you have a normally open contact, right?
Yeah.
Is that the only thing we have in there?
Yes. And the
That's
start
the only
switch.
thing that we're using is a normally open contact, which looks like this. Okay, here's our coil. And here is our contact. Let's just call it A, MA, and MB. Okay? Right at MA, we have power. We have no power at the coil. Right here, right there.
Uh-huh.
Okay? Is anything going to get from here to there?
No, not like that. But what I'm saying is I don't understand what activates the coil.
What activates the coil is when I press this.
But why? I guess I'm looking at the flow of the power, so it all goes through
Here,
the
I'll
top
show you.
and
I'll
then-
show you why.
and then comes back down. I guess I'm not sure how the coil itself activates. That's what's not clicking in my head.
Okay, let's consider this to be our neutral or ground, okay?
Okay.
What do I need to turn on that coil? I need to have a
Power.
plus to turn on that coil. So here's my start switch. And here's my plus sign. Okay, energy is going right to there. As soon as I press that start, energy flows through here, creates a magnetic field, which pulls this closed and allows this to do its thing. I hope you caught that.
Yeah, but see, I guess what I'm looking at is the coil's up there, and the way it's drawn, it looks like the contactor is actually wired to the open switch, and so to me it seems odd that I see what you're saying. Just the way it's drawn, to me it doesn't make any sense why they do it that way.
They do it that way so that everything is layered in rungs. Okay? This controls that because it says here's M, there's M. So there's the link between those two things. This could be in another planet. It's part of this device. Where'd that device go? It's part of this device that when I put power on that coil, this thing goes ka-chunk and physically connects these 2 points together.
I guess it's because the fact that the coil and the contactor don't look like they're connected that way.
They're connected magnetically.
I know, but it doesn't, to me, because I'm used to schematics, you know, the way it's drawn, it doesn't look like the coil is, you know, if they had the contactor under the coil, you know, over where the lamp is, that would have made more sense to me. That,
Yeah, but that's not the way it works.
but see, that's what I wasn't getting, is how come there's no power, why doesn't the power trip the coil?
Because they don't show this.
Yeah, see, that's what I wasn't getting. I wasn't figuring out
That's
why
the whole
you had-
relay aspect of it. We don't want them in the same place because we want to make sure that when I'm controlling this in my little room, that I'm not next to where all this is. So in the real world, what I might have is I might have a big wall between these things. So that this switch is controlling this coil, and then the coil is controlling the contacts.
And see, to me, it just seems backwards, because it's like,
Well, you're going to have to get over that.
yeah, this is why I said I did not get ladder logic when I was in the apprenticeship. When
Yeah.
you know, we touched on it. We barely did anything, but this
No.
is why it didn't make sense to me.
When you see something that looks like this, where you have an M and another M, that means that usually this is the symbol for the coil, and these are the contacts, and the coil controls the contacts magnetically.
That's where I was not getting it, was I wasn't seeing the motor as the coil, and I was looking for the activation of that contactor. So
Right.
that makes more sense. Okay.
All right, let's look at the top. Right here. Okay, what's going on here? Let me see if I can get this a little bit closer. You really want to talk about remote. It's bad enough that you weren't able to look at these in the same circuit, but now look what we have. Not only
Manual.
does this M control this set of contacts, but it also controls these contacts as well. Okay, notice that they're all labeled what? M.
M. Mm-hmm.
And here's that hooky little thing that's the overload part. That's this down here.
Yeah.
Here's the M. Here's the coil for the M. Here's the M switching. And here's the overload part, which is this part right here.
I think it would probably be easier. The bottom schematic or logic, that's for remote. The one up top is manual, because you got three
Well,
wires.
is that what it says in
L1, yeah. Mm-hmm.
Because, yeah, and you have a start and stop here.
Yeah.
Okay, so very similar. It's basically, this is here,
Yeah.
and this is what's added.
Yeah.
Right? This is actually part of this. There's your start and stop button. This is kind of showing you where they are on the board. So this is more of an assembly language or assembly drawing than this. This is more functional. This kind of shows you how everything's laid out. You have one box with a start stop in it. You have one box with a pilot light in it. And you'll also notice that these do not follow what we talk about in our 104 class. Right? Since when did we start using dashed lines to represent object lines in a drawing?
Yeah. It's showing you that's a control box.
So, you know, you have to kind of look at things with, you know, what are they trying to get across here? Well, the reason they don't use solid lines is because they're using solid lines for the circuit traces. And it would be very confusing to have a solid box around here. How are you going to separate those from each other? Right? So, you know, you do what you have to do to make things work in some cases. Sometimes what works in one industry doesn't always work in another industry. And when it comes to drawings and schematics and ladder logic, that is the case. Okay? But what you have to get through your head is that there doesn't have to be a pictorial connection between the M here and the M there, the M here wherever it is, and all of these other things. Okay? That's a long answer to your question, but I hope we figured out a couple things.
Yeah, connecting the M as being the coil, and basically in my mind it goes backwards, so that's okay. But that's what I was missing, was what's controlling the coil to not open.
Okay, yeah,
So,
it's the
yeah.
magnetism. That's the part that isn't shown.
Okay. Thank you.
Sure.
I hate
Terry, do you have any question?
Give me a schematic and I'm good.
That is a schematic, it's just a
Yeah,
different
in the Army they taught us the ladder logic, and what they taught us with it is that we identified
So
what
what's the-
components were in a specific circuit. So now that we knew those components were in that specific circuit, we can trace out that circuit on a schematic, and then we can follow it.
It is a little different, and you know, it's one of those kind of deals where if you're not used to it, it will take you a little while to get used to it.
Yeah.
But it's not difficult, it's just different. Okay?
Yeah.
All right, good deal. Let's take a break, and at 1:15, I will give you guys the diode quiz. It'll quiz on diodes today, right? Yeah.
Were you gonna do any vocabulary?
Probably. In the 1:45, we'll probably do that. As a matter of fact, I'm fine with giving you guys the vocabulary and doing that first and then giving you all the